All right, you'll recall where we left off was this first principles formula for working out how to differentiate. And let's face it, to use that every single time is a pain in the neck. But what maths is about is patterns, and once we can discover a pattern, that will make us do it quicker. So let's start discovering some rules that we can use to save some time. So we'll just start with y is some constant number. Now we've already seen what the answer is, but let's prove it. So if it's a constant number, function x is a constant, so is function x plus h. Putting it into our formula, we get c minus c over h, which of course is 0 everywhere. So from that we know we don't have to do this formula. Whenever we want to differentiate a constant, we know the answer is 0. We then moved on to lines. So some constant times x. So again, let's put it into our formula. Function x is kx. Function x plus h will end up being kx plus kh. Pop it into the formula. The kx's cancel. So do the h's. And we get a constant k. So whenever we differentiate something x, we know it's that thing. What about polynomials in general? X to the power of n. Need to remind you of something so I can prove this. We have, of course, seen difference of two squares, a minus b, a plus b. We expanded on that and said, hey, this is the difference of two cubes. A minus b, a squared plus ab plus b squared. And in fact, there was a pattern. Difference of two quartics could be written this way. A minus b, a cubed plus a squared b plus ab squared plus b cubed. And that pattern continues whenever you've got a to the power of n minus b to the power of n. You can always factorise it to be a minus b, and then in the second parentheses, the power of a go down by 1 each term, power of b go up by 1. It's that pattern that's going to be useful in our proof. So function x will be x to the power of n. Function x plus h is x plus h to the power of n. So when I put this into our formula, we have x plus h to the power of n minus x to the n. So it's that situation. Something to the power of n minus something else to the power of n. So I know this will be factorised. Now, the first parentheses will become x plus h minus x. In the second one, the powers of x plus h will be going down by 1. The powers of x will be going up by 1. But this is now good because it gets rid of the 0 on 0 idea, because x plus h minus x is of course h. And then the h cancels with the h, leaving us with just that second parenthesis. So that's it as h approaches 0. Well, let's substitute the 0 in. And look what happened. Every single one of those terms becomes x to the power of n minus 1. So the question becomes, how many x to the powers of n minus 1 are there? So let's go back to our pattern. When it was the power of 2, we had 2 terms in the second parentheses. When it was the power of 3, we had 3 terms. When it was power of 4, we had 4 terms. So it's fair enough to conclude from that we've got n lots of x to the n minus 1. And that now gives us a pattern to differentiate any polynomial we like. So we bring down the power, if you like, and then subtract 1 from the power. So just with those 3 rules, now we can differentiate any polynomial function that we like. So let's have a look at a few. Y equals 7. 7's a constant. So y dx is 0. A lot quicker than first principles. Y equals 37x. Aha! 37. X to the power of 10. This is the one we bring down that power. 10, lower the power, 9. 10x to the power of 9. So it becomes very quick, very efficient. So here's a quadratic, but the beauty of calculus is you can do it a term at a time. So when I differentiate the 3x squared, when I bring that 2 down, I've got to multiply the constant out the front as well. So we'll end up with 6x plus 6. 2x plus 1 squared. Now there is a rule that will allow us to do this even quicker, but I won't use that right now. I'll wait until we get to that. At this stage, okay, I'm going to have to expand it out. 4x squared plus 4x plus 1. Then it becomes 8x plus 4. So if function x is x cubed minus 3, find f dash 2. This is where we now got to be careful. Make sure you read it carefully. Big mistake people make here is just substitute 2 in because they miss the dash. They say, find function 2. Not what it's asking. It wants the gradient function, not the function. So first thing we do is go and find the gradient function. Differentiate x cubed, we get 3x squared. Now I can work out what f dash 2 is. There's 3 lots of 2 squared. we get the answer 12. Setting out now becomes really important. You don't just write down, 3x squared. You've got to distinguish between the two. This is the function, this is the gradient function. You label it so we know which one is which. Find the equation of the tangent to the curve, and this is a cubic of course, at the point 1, 1. There's my function, 5x cubed minus 6x squared plus 2. To find the equation of the tangent, I need the gradient function. So we differentiate 15x squared minus 12x. Now that's not the gradient, that's the function that allows us to find the gradient. We now need to tell it what point we're looking at. Well, I'm interested when x equals 1. Again, explain what you're doing. I've got my function, this is my gradient function. Now, I want to know when x equals 1, what is this gradient function? Substitute in and we get 3. So I know the slope I want for this question is 3. I got a point, I got a slope, point slope formula. So we sub it in, play around with it, and there it is in general form. 3x minus y minus 2 equals 0. Find the points on the curve, another cubic, where the tangents are horizontal. So where would the tangents be horizontal? Well, there's the function, there's the gradient function. What is this question asking me? When are the tangents horizontal? Well, the slope of horizontal lines is 0. So I want to know when is the gradient function equal to 0. Tangents will be horizontal when the gradient function is equal to 0. So we solve that. 3x squared minus 12 is 0. X is plus or minus 2. They haven't asked us for the x values, they want the points. So now I substitute back in. Be very careful when you substitute back in. I don't know how many times I've seen people substitute back into the derivative. Surprise, surprise, what do they get for the answer? 0. And they write down the points as negative 2, 0 and 2, 0. So make sure you are substituting into the correct function. A normal. It's another important line we have in coordinate geometry. A normal is a line that is perpendicular to a tangent at the point of contact. So here's a random curve. There's my tangent. So the normal at that point would come through at right angles. So that's what we call a normal. So if they ask us to find the equation of the normal, all right, there's my function, there's my gradient function. Now, I can't use the gradient function to immediately find the slope of the normal, but I can find the slope of the tangent. So I'll substitute in x equals 3 and I get 21, but that's the slope of the tangent. So the slope I want is perpendicular to that, negative inverse. So minus 1 on 21 would be the slope I'm looking for here. Got a point, got a slope, point slope formula. Oh, they're not nice numbers. How did I come up with these? Jeez. Well, 609, well, there it is in general form. X plus 21y minus 612 is equal to 0. A note about the setting out. You are actually solving an equation when you differentiate. It's no different to solving an equation. It's like what you do to one side, you do to the other. So when you see something like this, it's like solving an equation. You write the lines down, don't be lazy. So y equals x squared plus 2x. What I'm about to do is differentiate both sides with respect to x. Now, you wouldn't actually write it down like this, but this is what you're actually doing. What you do to one side, you do to the other. So I am differentiating on the left-hand side y with respect to x. On the right-hand side, I'm differentiating x squared plus 2x with respect to x. So on the left-hand side, what I'll end up with is dy dx, and on the right-hand side, I'll end up with 2x plus 2. But what's really happening is this. I can't differentiate y with respect to x, but I can differentiate it with respect to y. But I can't change the question, so now I balance it out by multiplying by dy dx. So if you like, the dy's cancel, and there's the dy with respect to x. We'll differentiate y with respect to y. What do you get? 1. So I have 1 times dy dx. We go to our answer. So as I say, we don't write that down, but that's what's actually happening when you're doing this differentiation. That idea is what's called implicit differentiation, and we'll look at that later in this particular topic. The other thing is match the notation that's being used. Remember, there's these different ways of writing the derivative, we said. So match it. So if they ask me this, y equals x squared plus 2x, I answer it with dy dx. Or maybe y dash, I could have done it that way. If they had said function x equals x squared plus 2x, then I say f dash x is 2x plus 2. Right? So match the notation. If they had said d x squared plus 2x dx, then it's simply, oh, well, that equals this. When I differentiate this with respect to x, I get this. So the setting out is important. Let's have a look at these ones, 9c and 9d.